So far, we have looked at, Aditya, some definitions. We have a displacement vector and a position vector. How do those differ? Displacement vector.
The position starts from the origin and the displacement runs from the point.
So a displacement vector can be between any 2 points, and the position vector always starts and goes back to our origin. We have defined a unit vector as a vector that has a length of 1 and is in a specific direction. Okay? We have learnt how to graphically and algebraically do arithmetic. Which ones have we done? We've done addition, subtraction, which is adding the opposite direction, and we've done multiplication by a scalar quantity. Now, I want to start today's lesson by talking about the multiplication by a scalar quantity. When we multiplied by a scalar quantity to a vector, what did we do to it?
Stretched it.
We stretched it or compressed it, depending on what we're doing. And if it was a negative, we headed it off in the other direction. But we didn't change the direction that it was acting in. We use two special unit vectors to define what direction that we're acting in. We've got an I and a J direction. And even though we link them in our heads to X and Y, they don't need to be X and Y. They just need to be perpendicular to each other. So we can decide where those are. We're all good so far? We didn't do division, all right? And it's not going to be part of the course. What we are going to do is something called a dot product. There are two main ways of multiplying vectors by each other. The first one is dot product, sometimes also called a scalar product, and I'll tell you why as we go on. The other one is called the cross product. The cross product isn't in the course, so we don't need to know the cross product. But if you come across it, it's not particularly hard. Now, while I was preparing for this, you guys know I haven't taught vectors before. I know how to do it, and I was getting really down because I knew how to crank the lever. I know and have used dot product for years. And I'm like, turn that lever, this is why it works. And you guys have the formulas on the formula sheet. But what I didn't kind of get around my head and what I was really searching for is how to get you guys to understand why we would do dot product. So I'm going to start by going through and giving you the formulas straight up, because the mechanics of the dot product are actually not hard. Tomorrow-ish, we'll be talking about how we can use that along with our cosine rule and how we developed these. But I wanted to get you guys to have a feel for why we would use the dot product. But I'm going to get over it, rip the band-aid off and say, this is what the dot product is. So, when we have a dot product, we have one vector and we have this floating dot. It's not a decimal, it's a floating dot, okay? And we have another vector. So one vector dot another vector. When we are doing this, we can do it in various formats. One of the most common ways of doing it is we're going to get, what am I going to do? Yep, that way. AX BX plus AY BY. And I'm using these to denote the X and the Y direction, or the orthogonal directions. So I'm getting us all of our A's in our X direction, all of the first bits in our X direction or our Y direction, and then in our J direction we will be adding those separately. There's another way of doing it, which is that we have the magnitude of vector A times the magnitude of vector B times the angle between the two vectors. And we're going to define the angle between the vectors as if we could line up our A and our B with their tails together. So it's really important that their tails are together. So we've defined an angle between two vectors, and we've defined two ways of doing the dot product. Okay, so let's turn the handle. if I gave you two column vectors that were 3, 1, and I want a dot with -2, -2, we are collecting the things that are in the same direction. So in the same direction, oh, actually I'm going to make that one different just so we have all different numbers. In the same direction, which are my components that are in the same direction? I've denoted them as x's here, but they don't need to be. 3 and -2 plus 1 and -4. I get -6, -4, and my answer is -10. So I had two vectors. I've applied the dot product to them. I've utilized this component form of them. I collected all the x's together. I collected all the y's together. And I've come up with a number, -10. Not a vector, a number. And because we come up with a number, we often also call this the scalar product, because our product is going to be a number. So see, crank the handle, easy peasy, out it pops. I can do this. I could actually find the angle between the two of them because I can work out the magnitude of A and I can work out the magnitude of B, and I can divide my dot product to get cos, which gives us a different form of the rule. Cos theta is going to be my new dot product divided by the magnitude of A times the magnitude of B. And I can find the angle between them. I can crank the handle and I can work out what it is. But what does this mean? Why would we do this, and why do we want to get a scalar number out? And this is where I went searching, because I thought if I can't explain a gut feeling for you guys, an intuition on why we do this, then you're not going to remember it. You can look up the formula and you can work it out, but as soon as I give you a curly question, you're going to be like, yeah, curly question, I don't know the answer to it. So when we think of dot product, the best way that I've come up with thus far, I'm hoping to come up with more, and I was saying to Mr. Wu this morning that every time I teach something to you guys, I come up with a better way to explain it. So next year's I'll teach better than you guys, but you'll bear with me, is we want to see what kind of boost each vector has on the other vector in specific directions. So the boost that these vectors have on each other is they make each other 10 times stronger, but shooting off in the opposite direction. Okay? The analogy that I came up with that I thought was really quite good is, who has played Mario Kart on there? Yes. Yes? What happens when you go over those boost pads? You go faster, agreed? What happens if you go over the boost pads at an angle? You don't go straight, you get a boost, right? But you get a boost in a weird way. And that is your scalar product. It's the weird way that the boost goes. If you are approaching something with no angle between our two vectors, you're going to get maximum boost off those. If you go over a boost mat backwards, what happens? You're going to, well, you're either going to be in the opposite direction or you're going to grind to a halt, but there's going to be a bit of a force back on it. If you go over it at an angle, you get some boost, but not the maximum amount of boost. And the scalar product looks and says, well, in the direction you were meant to be going, you got this much boost, but you also got this much boost in this direction. And overall, that means you've got this much boost. Okay? And it's just talking about what's happened and what effect have these vectors had on each other. We good with that? I looked at it and I went, that is spot on, perfect. So when we talk about boost, I'm going to start with two vectors. Let's go back and have a look why this works. If I have a vector A and at another angle a vector B, I'm looking for the boost that each of them have on the other one. So I can do this in two ways. I can break it into I's and J's because we know that we have I's and J's for these. or in this case, I'm calling them x's and y's. So I can break up my A into this much in the x-ish direction and, same colour, this much in the y direction. And I can break up my B to this much in the x-ish direction and this much in that y-ish direction. Doesn't matter the directions as long as they're perpendicular to each other. So I'm now boosting this vector in the x-ish direction by another vector in the x-ish direction. These two are being multiplied together. AX, BX. And then I'm adding to them the boost that I have in the y direction, AY and BY, not quite the right lengths. And this is what is happening when we get our dot product. I could also say, ignore my x-ishes and y-ishes directions, method 1. Just see how much boost A gives to B. And I can actually change my components to be in that B direction and in the A direction. To be in the A direction, I'm going to draw another diagram. Here's my A direction and here's my B. Again, must be perpendicular. I'm only interested in this boost because this boost in the perpendicular direction has no effect on my B. Do you agree? It has no impact on what's happening to this B. It's happening perpendicularly to it, and we'll come up with some rules. To get how much this is, if this is my A vector, this is my angle, using trig, what's this red vector down here? Or it's not a vector anymore. What's this red quantity down here? It's going to be the magnitude of A times cos theta. Agreed? So that's the direction that's impacting B. And because I'm acting entirely in the B direction, B becomes a scalar as well. So I get the magnitude of B multiplied by the magnitude of A times cos theta. And there we get our other formula. So we have our breakup of into components, or we have our breakup where we just see what effect one has on the other vector. We okay so far? So let's pull out a couple of rules about vectors and see if we can work our way through them and see if I'm covering everything. Okay. I want to analyze the result. So we're going to call it analyzing the result. What happens if my two vectors do a dot product and there's no impact on each other? My resultant on the dot product is 0. What do you think that tells us? They're perpendicular. Nice. There's one other thing they could be. Or, there we go. Either A or B is a 0 vector. Perpendicular, because if you're heading that way and somebody else is heading this way, they're having no impact on you at all. Okay, so if we're perpendicular, we end up with a 0 product. Let's look at the formula and see why that might be. Perpendicular means my theta is. Perpendicular means my theta between them is 90. What's cos 90? 0. 0. We're done. What happens if our product is positive? So we get a positive number in some shape or form. What is that telling us if my scalar product, my dot product, is positive?
They're going in the same direction.
Excellent. There is growth. Now I'm just going to call it growth because either I'm going to get bigger, or if it's a fraction, it's going to be slightly smaller. But there's growth in the same direction. My blue is running out, so I'll have to transition. i.e., theta has to be between 0 and 90 degrees. We okay with that? So I've got to be heading in the same direction, and my angle has to be between 0 and 90 degrees there. What happens if I am negative? We had one that was negative. Think about what my angle would have to be. So 90 between the two things, we had no effect on each other. Less than 90, there was some effect, and because it was in the same direction, it grew. More than 90, is there some effect on the two vectors? There is, but it's in the opposite direction to each other. So, growth in the opposite direction.
What is your definition of growth?
It means a change in magnitude. For me, that's how I'm using it in this context. So that's why it's growth in inverted commas, because it might not be getting bigger, but it's getting a boost. All right. Now, we've got a couple of special conditions, okay? Our special conditions are 0 degrees. I should write theta equals 0 degrees. And our other special condition is theta equals 180 degrees. Now, I haven't talked about an angle between two vectors being more than 180 degrees. Can anyone suggest why?
Just in the opposite direction.
So if we had a vector and another vector where the angle between them was more than 180 degrees, you go and do the other one. So we define the angle between the vectors as being the non-reflex angle, which is why we only need to go to 180 degrees. We okay? Now, either by looking at your formulas or your intuition, what happens when both our vectors have an angle between them of 0? What's happening? Where's our Mario Kart analogy? We have our maximum boost. And they must be in the same direction. So let's extend that to what happens when we are 180 degrees from each other. We're not going to get much boost, are we? But we're in the opposite direction. So we're going to write down that we're in the opposite direction. How much boost we get might depend on which one's bigger. Right, are we okay with this so far? So we use this to not worry too much about direction, but worry about what sort of effect our vectors are having on each other in some specified direction, usually the direction of one of those vectors. Like I said, as soon as I got the Mario Kart thing, it was like, oh, I know exactly what happens when I go over that Mario Kart boost pad.